The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next presenter is James Lafikes. He has a BS in Civil Engineering from University of Missouri in St. Louis and an MS in Civil Engineering from University of Kansas, and it's currently pursuing a PhD at KU.
Good afternoon. Thank you all for being here today, and thank you to the committees who are helping sponsor this session too. I want to start out by first acknowledging the other folks who have gone through our research group and have done a significant amount of work in the settlement cracking studies that we've done over the past several years. So Ryan and Osama helped develop a test procedure that we've been using, and Eman has gone through quite a few different series of mixtures in pursuit of her PhD. So we wouldn't be here, or I wouldn't be here if it weren't for their work. We also have a lot of sponsors who help contribute funds for our research, and I'll highlight the 19 state DOTs along with FHWA who come together and contribute to a pooled fund study. What I'll be talking about today is introducing the concept of settlement cracking, introduce the laboratory test that we developed at KU to evaluate qualitatively different crack reduction technologies and their effect on sediment cracking, have some selected results that I'll be showing, and hopefully tying everything together with a summary. So, significance of bridge deck cracking. If we're going to repair or replace all affected bridge decks within our infrastructure system, that's going to be billions of dollars, and this accounts for hundreds of millions of traffic trips across the affected structures annually, so that's quite a problem we're facing here. Main issue with cracking, especially settlement cracking, is that when you have cracks developing directly over reinforcing steel, that's a direct path for de-icing salts and other corrosive chemicals to quickly penetrate down to that steel, and you have earlier initiation of corrosion and accelerated corrosion rates, which will even further deteriorate your structures. And for any water that penetrates down in there for freeze-thaw prone regions, you can have damage due to that too. So main culprits of cracking that we deal with in our research are both in the plastic and hardened state of concrete. So we have plastic shrinkage and settlement in our plastic state, and after the concrete hardens, we deal with drying and thermal mechanisms there. But for this presentation, we're focusing primarily on settlement cracking. So here's a cross-section of a piece of reinforced concrete with a piece of reinforcing steel in the middle. This steel acts as a restraint in our cross-section here. So after fresh concrete is placed within our forms, it's going to flow over that piece of rebar. And the mechanism of settlement cracking is that you have the solid particles in this mixture settling down to the bottom, and then you have bleed water rising to the top. And as that concrete hardens, you have local tensile stresses that develop in the top and make you more prone to have cracking directly over those bars. Not a good thing. So, factors that affect settlement cracking, there's a lot of previous research that has been done in this area showing that increased slump for a given mixture can also increase settlement cracking. On the design side of things, we can help mitigate settlement cracking by increasing concrete cover and decreasing bar size. And you have detrimental effects, potentially vice versa. So bigger bars, that's a bigger surface area for that concrete to flow over, and less cover makes it more likely that that concrete's going to crack. And finally, on the research side of things, we're tying settlement cracking in with shrinkage of concrete. And spoiler alert, main point of this presentation is to show that many of the crack reduction technologies that are available to help reduce shrinkage also reduce settlement cracking. Now getting into the laboratory side of things. So this is a test, again, that we developed at KU. to qualitatively compare different crack reduction technologies against a 100% Portland cement mixture in terms of settlement cracking performance. Geometry of these specimens, we cast 12-inch by 12-inch by 8-inch deep beams. We cast those with a single number 6 bar with 1 1/8 inch of cover over the top of that. And after casting, we place these specimens in an environmentally controlled room for 1 day of curing, 50% plus or minus 5% humidity, and 73 plus or minus 3 degrees Fahrenheit. And here we have just a diagram of our settlement cracking specimens. So to hold the rebar in place, we drill and tap both ends of the bar and hold it in place in the mold with a machine screw. So for the properties that we're looking for in our concrete mixes before we actually cast specimens is we want to have an air content between 6.5% and 9.5%, concrete temperature between 71 and 75 degrees Fahrenheit, and then our independent variable that we use in these studies is the slumps. So most of our series vary the slump between 2 and 9 inches. And this is getting into probably the most important part for maintaining control and getting good data out of this is when we do a series, it's best to use a single operator for placing, finishing, curing, and doing the subsequent evaluation of each of these mixes. So procedure we use for that is we fill our forms in 2 lifts, vibrating between each one. We follow that with a plywood screed and then a hand float. And here's some pictures of the process. So there's filling and vibrating each layer and finishing. And the figure on the right is part of our curing regime, which was one of the things that was really important in the evolution of this test procedure. So one of the things we do after we finish the surface of these specimens is we place a sloped piece of plexiglass over the top. And this is to help mitigate other factors that can come into play in that first 24 hours that can cause cracking. So we just want to isolate settlement cracking by itself and not have drying shrinkage or any other issues with surface defects come into play. So we also want to make sure that we maintain a high humidity during curing, and we can verify this with temperature and humidity sensors that we place on the forms, and we can monitor that throughout the curing period. And after we place that sloped plexiglass on top of the forms, we seal those with a plastic sheet and seal that off with a rubber band. So not very complicated. And after 24 hours, we measure both the length and width of each resultant crack. So here's the finished product. So it's also important to note that the only cracks that we're actually counting are the ones that develop directly over the surface of that piece of rebar. So mixture proportions that we use in our study, or for each of these series, that we kept constant is a 0.45 water to cementitious materials ratio. We use 27% paste content, and for our 100% Portland mixes, which is our control series, that converts to 593 pounds of cement and 267 pounds of water. And to get our air correct, we use an air entraining admixture, and to vary the slump, we use a superplasticizer. Again, with our control mix, along with other ones, we use KU Mix, which is a mix design optimization program. And the aggregates we use with that are 2 gradations of granite, one with a 3/4 inch max size aggregate down to 1/2 inch, and then the other gradation is 3/8 down to number 8. We also use an intermediate size aggregate in the form of pea gravel. And for mixtures that we want to incorporate internal curing into, we use a pre-wetted pea gravel size lightweight aggregate and Kansas River sand for our fine aggregate. For our test program that we want to compare to our control mixes, we're looking at doing a partial replacement of cement with supplementary cementitious materials. So our binary mixes are 30% slag by volume, and our ternary mixes are 30% slag and 3% silica fume. And I introduced internal curing, but again, that's with a pre-wetted pea gravel size lightweight aggregate. And we proportion this material to achieve 7 pounds per 100 pounds of cementitious material of internal curing water. And we also repeat those SCM mixes with internal curing to see if we can get a combined effect. And we do. So additionally, other parameters that we looked at were incorporating a viscosity-modifying admixture and a shrinkage-reducing admixture. We also looked at 3 different types of macrofibers and 1 type of microfiber for which we varied the dosage on. And now getting into the results. Here's an example of one of our control series. For each of these graphs, we have slump on the x-axis and the ratio of crack length to bar length on the y-axis. So if each one of our specimens or in a single mixture had a crack 12 inches long over the entire length of the bar, that ratio would be 1.0. So I also want to point out that each data point here is the average of 3 specimens that we do per mixture. And it's important because we do get a lot of scatter with these series that we make sure we do enough mixtures in order to make sure we're getting a good trend line out of that. So getting into our comparisons now, both of these mixes are 100% Portland cement, but the series in red has that partial replacement of lightweight aggregate pre-wetted to provide 7 pounds per hundredweight of IC water. And for each slump that we looked at, we did see a reduction in settlement cracking. Mechanism behind that is that the bleed water that's going to rise up in the system can be pulled out of those lightweight aggregate pores a lot easier than from the cement matrix. So the bleed water that comes out isn't being taken from the cement at all. We see a similar trend with our binary mix. So when we have our 30% slag mixture, we also see a reduction in settlement cracking. Mechanism behind that is that you're tying up more of that bleed water in a finer granules of that SCM. And when we add 7 pounds per hundredweight of internal curing water, we see an additional reduction in settlement cracking at a given slump. And we see a significant reduction when we have a ternary mix. So with 30% slag, 3% silica fume, this is getting towards the limitations of our tests with, on average, less than 1 inch of settlement cracking per specimen. And finally, when we add 7 pounds per hundredweight to our ternary mixture, we also have a very low resultant settlement cracking result. And for that same control, when we dosed a shrinkage-reducing admixture, we used a dosage rate of 2% of cementitious materials by weight. And this is for 100% Portland cement. We also see a reduction in settlement cracking. This is likely due to, at early ages, SRAs causing swelling in the first 24 hours. For the series that we looked at the VMA with, we used a different control there, so that's why we have a different line and different numbers there to present. But for a mix that's more cohesive when you add a VMA to it, it's something that will behave like it has a higher slump than it actually does, we can see some benefits in terms of settlement cracking. Getting into our fibers, when we dosed 3 pounds per cubic yard with one of our macrofibers, we saw that for each given slump that we looked at, we had a reduction in settlement cracking. Very similar results when we used 1.5 pounds per yard of microfiber. And when we group all of our fiber results together, we see a very tight spread of data for each type and each dosage. And I'll point out that the 3 pounds and 1.5 pounds of microfiber per yard have almost the same result. The differences are not statistically significant. And finally, wrapping up, we've shown that settlement cracking does increase with slump, and that for the fiber series that we looked at, that the dosage rate doesn't necessarily change the behavior of settlement cracking, at least for the series that we investigated, and that we do have combined effects with SCMs and internal curing. And the most important takeaway for this presentation is that many of the technologies that are available to help reduce shrinkage in concrete mixtures can also reduce settlement cracking. So I'm happy to answer any questions. Thank you.
Two questions. First, maybe you said so. Did you say how you adjusted your slump? Was it by changing your water, or was it by changing your water-reducing admixture?
We varied super dosage to change slump.
Okay. And then the second question, you said that you only documented, or you only counted cracking that occurred over the bar that was in that your test specimens?
Right.
Did you either verify that no other cracks formed elsewhere, or did you measure those, document those so that you could calibrate your results of what cracks were occurring over the bar to make sure you were
for a finer
adjusting?
adjustment, yes. For a finer adjustment, if it's directly above the rebar or just adjacent to it, we took the cosine of the angle that we estimate to get a more accurate reading there. But for the most part, with our curing regime, we're able to isolate virtually all of that cracking to be settlement cracking or directly over that rebar.
Okay, so you just didn't have other cracks elsewhere in the specimens?
Right.
Okay.
Substantially, yes.
Great work.
Thank you.
Especially for those of us in the trenches. That's terrific and well presented. Two quick things. One is I noticed the design error was 8%, plus or minus 1.5, right? In other words,
correct.
it was 8. Well, why quite so high? Because I see that the higher the error, the less likely I'm likely to see plastic settlement cracks.
Good. That's a good point. We tried to keep consistent as much as we could with KDOT, or Kansas DOT, low cracking, high performance concrete specifications, which that's our air content range for there. It's 8% plus or minus 1.
Well, I like 8%. It's just that so many times we don't see them in many of the DOTs and in the private sector. Second thing is that, once again, I really like what you did. It's good stuff. I want to, in future work, you may want to take another look at SCMs and their effect. I typically tend to see more plastic settlement cracking in the as with SCMs and with higher dosages, and but that's that's out on actual bridge decks, other types of suspended slabs. Excellent, thank you very much.
Thank you. Good points.
I just wonder if you had done any theoretical or modeling because I know that in the soil mechanics there is a settlement that we can actually use here for actually getting ideas about how much settlement we get in concrete. I'm just wondering if you had a chance to look at that and compare that with the volume of cracking in general, like to find if there is a correlation or not.
No, we haven't done any theoretical modeling with these mixtures or this research yet, but